Our universe may have started as a question, not an answer. The moment of creation, the Big Bang, is often pictured as a single, definite explosion from a point. But what if that picture is fundamentally wrong? What if, in its very first instant, reality itself could not decide what to be? This is the audacious idea at the edge of modern physics, that the cosmos was born in a state of quantum superposition. It means the entire universe was the first and ultimate quantum object, existing in multiple potential states simultaneously before somehow choosing the one we live in today. By the end of this journey, you will have explored 30 of the most groundbreaking theories trying to explain this primordial maybe. We will see how the universe's first moment might connect to parallel worlds, to the nature of time, and even to our own consciousness. The story of everything begins with a cosmic coin toss that is still spinning. What do you think decided the outcome to grasp this radical idea? We need a simple but powerful thought experiment, one that lies at the very heart of quantum weirdness. Picture a barrier with two narrow vertical slits cut into it. Behind it is a screen that lights up when particles hit it. Now, fire tiny particles like electrons one at a time toward the barrier. You might expect each electron to go through either the left slit or the right slit, creating two neat clusters of impacts on the screen. But that is not what happens. Instead, over time, a pattern emerges, an interference pattern of alternating light and dark bands. This pattern is the unmistakable signature of a wave, like ripples on a pond. It means each individual electron did not choose a single slit. Somehow, it behaved as if it passed through both slits at once, interfering with itself. This is the famous double-slit experiment, and it demonstrates that a quantum object can exist in a superposition of multiple possible paths. Now, stretch that concept to the grandest scale imaginable. Theory number 1, often championed by physicists like Andre Lind, suggests our entire universe began as a cosmic version of that experiment. The initial conditions of reality, the very laws and constants that would govern everything, were not set in stone. They existed in a shimmering quantum haze, a superposition of countless possible configurations. One potential universe might have had stronger gravity, another might have had no electromagnetism at all. In this view, the Big Bang was not a single, definite explosion. It was more like a probability wave of all possible explosions, all trying to happen at once. Our specific cosmos, with its particular blend of forces and particles, was just one possibility in that vast quantum menu. So how did we get from that cosmic maybe to the definite world we see around us? The theory points to a process called decoherence, or a cosmic observation. Just as measuring which slit an electron goes through collapses its wave function into a single path, something caused the universe's quantum possibilities to collapse into our single, tangible reality. This collapse might have been triggered by the universe's own rapid expansion during inflation, or by some as yet unknown observer. The implication is staggering: our universe is not special or inevitable. It is simply the one that happened to be chosen when the first cosmic quantum dice stopped rolling. But what is this nothing that could give birth to everything? In our everyday experience, nothing means empty space, a complete and total void. Yet, according to quantum field theory, the most accurate description of reality we have, that kind of perfect nothingness is impossible. Even in what we call a vacuum at the tiniest scales, space is not empty. It is a restless, seething sea of potential. This is the quantum vacuum, and it is the foundation for theory number 2, the universe as a quantum fluctuation of nothingness. Here, Heisenberg's uncertainty principle takes center stage. This principle states, in simple terms, that you cannot precisely know both the energy of a system and the time over which that energy exists. There is always a fundamental fuzziness, a trade-off. This leads to a bizarre but proven consequence. Particles can pop into and out of existence from seemingly nowhere. borrowing energy from the vacuum for fleeting moments before vanishing again. These are called virtual particles, and they are the quantum foam that constitutes the fabric of empty space. Now, take that concept to its ultimate extreme. The universe's very first superposition, according to this theory, was not between different kinds of universes, but between two profoundly different states, absolute nothingness on one hand, and a tiny, embryonic speck of spacetime on the other. In that first indescribable moment, reality was in a quantum haze, fluctuating between being and not being. It was a cosmic maybe, balanced on the knife's edge of existence itself. This superposition was inherently unstable, a precarious state that could not last. Through a process still not fully understood, perhaps triggered by a random quantum jump or a tunneling event, the scale tipped. The fluctuation did not simply vanish back into nothing. Instead, it became locked in, a bubble of something that inflated catastrophically into the universe we know. In this view, our entire cosmos is the ultimate free lunch, a grand and permanent fluctuation in an eternal, restless quantum field. This quantum haze of being and not being presents a new puzzle, one that challenges our most basic experience. We perceive the universe unfolding in time, a steady march from past to future. But what if time, as we know it, is not a fundamental feature of reality, but an illusion that emerged from that first great quantum shift? This brings us to theory number 3, born from the formidable Wheeler-DeWitt equation. In the 1960s, physicists John Wheeler and Bryce DeWitt attempted to write an equation that would describe the entire cosmos using the rules of quantum mechanics. They succeeded, but with a shocking result. Their master equation, the wave function of the universe, contained no variable for time at all. It described a universe frozen in a single, eternal moment. This suggests that in its most fundamental state, the newborn cosmos was not a thing evolving in time, but a timeless superposition of every possible configuration all at once. Picture not a movie playing, but every single frame of that movie laid out simultaneously. A cosmic photograph where every potential arrangement of matter and energy coexists in a quantum blur. This is the profound implication of the Wheeler-DeWitt equation. The universe's first superposition was not just over what it could be, but over every possible when. In this view, time as we feel it passing is not a river flowing, but a story we are telling ourselves. It emerged, according to physicists like Carlo Rovelli, from the process of decoherence. As the universe's quantum possibilities interacted with each other, as that timeless wave function collapsed or branched, the illusion of sequence was born. One configuration became correlated with another, creating the chain of cause and effect we call history. So the ticking of the cosmic clock, the expansion of space, the very arrow of time, might all be side effects of the universe settling down from its original, timeless quantum dream into the single, sequential reality we inhabit. Our past, present, and future were all present in that first instant, waiting to be untangled. If the universe's first state was a timeless superposition of every possible configuration, then what happened to all those other possibilities? Did they simply vanish when our reality was chosen? According to the most radical answer, they did not vanish at all. They all became real. This is theory number 4, the many worlds interpretation's first branch. Proposed by physicist Hugh Everett in the 1950s, this idea rejects the notion of a wave function collapse entirely. Instead, it proposes that every single quantum possibility contained within a superposition is realized. When a quantum system interacts with its environment, it does not pick one state, it decoheres. This process effectively separates the possibilities, but instead of one being erased, each one continues on its own path, now in a separate, non-interacting branch of reality. Apply this to the universe's first quantum moment. In this view, that primordial superposition never collapsed. There was no single cosmic dice roll. Instead, the instant the universe began to decohere, it fractured. The very first quantum event caused the entire cosmos to split, not into two, but into a staggering multitude of parallel realities. Each branch represented one of the countless possibilities that existed in that initial haze. So what did that first split look like? It was not a trivial difference. It was the ultimate fork in the road of existence. One branch might have taken a path where the strength of the nuclear force was a fraction weaker, preventing stars from ever forming. Another branch might have crystallized with an extra dimension of space, or with gravity being repulsive instead of attractive. In one branch, the cosmological constant that drives the universe's expansion could have been so large that spacetime ripped itself apart in a flash. In another, it might have been precisely zero, leading to a cosmos that collapsed back on itself almost immediately. Our universe, with its seemingly finely tuned constants that allow for galaxies, planets, and life, is just one leaf on an infinite, growing tree. The scale of this resulting multiverse is beyond human comprehension. Every quantum event that has ever happened, from the decay of a single atom to every choice ever made, has spawned new branches. The multiverse is not a static collection of alternate Earths. It is an explosively proliferating fractal of every possible history unfolding simultaneously. In this breathtaking vision, the first moment of creation was not the beginning of one story, but the opening sentence of every story that could ever be written. The infinite branching of the many worlds offers a dizzying vision of creation, but it leaves one profound mystery untouched. Where did that initial wave of possibilities, that first quantum haze, come from in the first place? Another school of thought provides a startling answer. Our universe did not come from nothing, but from something else entirely. This is theory number 5, loop quantum cosmology's great cosmic bounce. While general relativity predicts the Big Bang began at a point of infinite density, a true singularity where the laws of physics break down, loop quantum gravity offers a different path. This theory proposes that space itself is not infinitely divisible, but is woven from tiny, indivisible threads, a fabric of spacetime with a fundamental graininess. This quantum structure changes everything about the moment of origin. In this view, our universe's first superposition was not a choice between being and nothingness. Instead, it was a quantum bridge between two classical, tangible realities. Picture a universe, perhaps very much like our own, growing old and cold, its expansion long since reversed by the pull of gravity. It collapses inward, galaxies merging, temperatures and densities soaring to unimaginable levels. In classical physics, this collapse would end in a crushing singularity, a final dot of infinite density. But loop quantum gravity intervenes. As the density reaches the Planck scale, the fabric of spacetime, woven from those finite loops, cannot be compressed further. The repulsive force of quantum geometry becomes overwhelming. The collapsing universe does not hit a wall, it undergoes a quantum transition. In that critical moment, the universe exists in a superposition of two states, the final, ultra-compressed moment of the old cosmos and the first, explosive moment of a new one. It is a cosmic quantum tunnel, where the dying breath of one reality becomes the first cry of another. This superposition is not of creation, but of transformation, a probabilistic bridge across what would have been a singularity. The Big Bang was not a beginning, but a bounce, a great cosmic rebound smoothed out by the fuzzy probabilities of quantum geometry. Our entire history, from the first stars to this very moment, may simply be one phase in an endless, cyclical dance of universes, each birth connected to a prior death by a fleeting quantum maybe. The endless cycle of cosmic bounces presents a universe with no true beginning, yet our own reality feels uniquely definite. Where did this particularity, this specific set of laws and history, come from? Another revolutionary idea suggests the answer is written on the walls of reality itself. This is theory number 6, the holographic principles encoded Genesis. In the 1990s, Physicists like Leonard Susskind and Juan Maldacena made a discovery that sounds like pure science fiction. They found compelling evidence that all the information contained within a volume of space, including the three-dimensional objects within it, and even gravity itself, can be completely described by information encoded on the two-dimensional boundaries surrounding that space. Think of a hologram on your credit card, a flat, shimmering sticker that, when tilted, reveals a startlingly three-dimensional image. The holographic principle proposes our universe works the same way. The rich, three-dimensional cosmos we experience, with its stars, planets, and galaxies, might be a grand projection from a vast, two-dimensional surface at the edge of everything. Now, apply this to the first moment. In this view, the universe's initial quantum superposition was not a haze of three-dimensional possibilities. It was a quantum blur of every possible two-dimensional code, every conceivable pattern of information that could be written on a primordial surface. This surface, perhaps the cosmic horizon of the infant universe, was a flickering screen of ultimate potential. Each possible holographic pattern represented a completely different projected reality, a different universe with its own physics and history. Our universe's specific laws of nature, the strength of its forces, the number of dimensions, were not written in stone at the beginning. They were written in quantum code, one pattern among an infinite number of others shimmering in superposition. The emergence of our definite cosmos was the decoherence and selection of one specific holographic pattern from that quantum menu. When that particular code was somehow stabilized and projected, it gave rise to the three-dimensional expansion we call the Big Bang, complete with the illusion of gravity and matter. In this breathtaking framework, the entire history of our universe, from the first quark to the last galaxy, is like a movie being played back from a single, chosen cosmic DVD. The projection is so perfect, so complete, that we, living within it, can never tell we are watching the show from inside the screen. Yet if our universe is a holographic projection, what happens when the projector finally shuts off? At the end of time, in a cosmos grown unfathomably cold and dark, all matter may decay into radiation, all black holes may evaporate, and the universe could become an endless, featureless sea of low-energy photons drifting forever apart. According to the great physicist Roger Penrose, this is not an end, but a gateway. His theory, conformal cyclic cosmology, proposes an endless cycle of cosmic eons, each beginning with its own Big Bang. The key lies in the concept of conformal geometry, which ignores scale and focuses only on shape and angles. In the far, far future, when the universe has expanded to near infinity and contains no massive particles to define a scale, it becomes effectively timeless and smooth, a state mathematically identical to the high-energy, ultra-smooth state of the Big Bang itself. This is the profound twist. The infinite future of one eon becomes the infinite past of the next. But how does the information from our universe, all its structure and history, get erased to make way for a new one? Penrose suggests the transition point between eons is not a classical bridge, but a quantum gravitational blur. At the moment of crossover, when the old universe is maximally expanded and the new one is about to burst forth, reality enters a state of quantum superposition. All the specific details, every star and story, are lost. What remains is only the conformal shape, the pure geometric pattern of the cosmos stripped of all scale and matter. This pattern, however, is not a single blueprint. It exists in a superposition of all possible ways its fundamental conformal data could be reshuffled. Think of it like a cosmic deck of cards where every card is a fundamental geometric relationship. At the transition, the deck is not in one order, but in a quantum haze of every possible ordering simultaneously. The birth of the next Big Bang is the collapse of that superposition, the selection of one specific reshuffling from the quantum possibilities. This single quantum gravitational event determines the fundamental constants, the initial conditions, and even the dimensionality of the next universe. Our cosmos, with its particular laws, might be just one random hand dealt from an eternal quantum deck. In this vision, the universe's first quantum moment is not a singular event at the dawn of time, but a recurring ritual at the boundary between death and rebirth, where everything is forgotten so that something new can begin. The transition between cosmic eons presents a universe reborn from pure geometry. But where did the geometry itself come from? A different idea suggests the answer lies not in cosmic cycles, but in a process of cosmic survival of the fittest. This is theory number 8, the quantum Darwinism of cosmic selection. In our everyday world, objects seem to have definite properties. A table is solid, a planet orbits a star. But quantum mechanics tells us that at the most fundamental level, these properties are not inherent. They become objective through a process of communication. Quantum Darwinism proposes that when a quantum system interacts with its environment, its many possible states do not all get copied equally. Only the most robust, stable states are redundantly imprinted onto the environment, like countless witnesses all agreeing on the same story. These are the states we perceive as real. A simple example is the location of a dust particle in a sunbeam. The particle interacts with trillions of photons, and all those photons carry the same information. The particle is here, not there. That redundant copying makes the particle's position an objective fact for anyone who cares to look. Now, apply this radical filter to the universe's first moment. That primordial quantum superposition was not just a menu of possibilities, it was a cosmic competition. It contained every conceivable set of physical laws, every potential configuration of dimensions and forces, from the wildly unstable to the eternally barren. But only a tiny fraction of those potential universes possessed the right qualities to be redundantly copied. What were those qualities? They were the hallmarks of durability and complexity. A universe where the nuclear forces were too weak might never form atoms, collapsing back into a haze of particles before any structure could be imprinted. A universe where gravity was too strong might crunch into a singularity instantly, leaving no environment to record its existence. The winning candidates, the ones that became our reality, were those rare superpositions that were stable enough to persist, expansive enough to create a vast environment, and complex enough to generate countless interactions that would redundantly copy their fundamental laws into the fabric of spacetime itself. In this view, the emergence of our specific cosmos was not a random collapse or a conscious choice. It was a form of cosmic natural selection. The quantum states that could produce galaxies, stars, and eventually observers were the ones most fit to be copied and made objective. Our universe's finely tuned constants are not a lucky accident. They are the signature of a winner in the first and greatest quantum competition. A set of laws so robust and self-reinforcing that they wrote themselves into existence by creating the very observers who would one day discover them. Quantum Darwinism suggests our universe won a competition by being observable, but this raises a deeper, almost philosophical question. Who or what does the observing? This brings us to a theory so mind-bending it seems to invert causality itself. John Archibald Wheeler's participatory anthropic principle. Wheeler, the physicist who helped coin the term black hole, proposed that the universe only becomes real through the act of observation. He famously described it as a participatory universe. Apply this radical idea to the very first moment. In this view, the universe's initial quantum superposition, that haze of every possible configuration, did not collapse in the first instant. It persisted unresolved for billions of years. The entire cosmos remained in a state of shimmering potential, a cosmic question waiting for an answer. That answer, according to Wheeler, came with the arrival of the first observer. Not a god or a cosmic entity, but something that emerged from the universe itself, conscious life. The first act of observation, perhaps by a primitive organism sensing light, or much later by a scientist peering through a telescope, retroactively collapse the wave function of the entire universe all the way back to the Big Bang. This is the staggering implication of retrocausality, where an effect in the present can influence a cause in the past. Our observation today does not just measure the universe, it helps select which universe came into being. Think of it as a cosmic version of a multiple-choice test, where the answers you circle today determine what questions were written at the beginning of time. The universe's finely tuned constants, the specific arrangement of matter that allowed for galaxies and planets and life, were not set in stone at the beginning. They were a set of possibilities that only became definite when a conscious entity finally looked back and, in a sense, chose them. This creates a closed, self-justifying loop of causality. The universe exists in a certain way because we are here to observe it, and we are here to observe it because the universe exists in that certain way. It is a cosmic handshake across 13.8 billion years, where the ending and the beginning define each other. In this participatory vision, we are not just passive inhabitants of a finished cosmos. We are active participants in its creation, our consciousness reaching back through the eons to give solidity to the first quantum dream. The participatory universe suggests our observation carves reality from the quantum past, but this demands a stable past to observe in the first place. Where did the very structure of past and future come from? This leads us to a theory that dissolves time into something far more subtle. Theory number 10, the thermal time hypothesis origin. Proposed by physicist Carlo Rovelli, this idea turns our intuition on its head. Time is not a fundamental river in which events float. Instead, time is a thermodynamic artifact, a story told by disorder. To understand this, picture a cup of hot coffee left on a counter. It gradually cools to room temperature, its heat dissipating into the air. This process is irreversible. It defines an arrow from the ordered state of hot coffee and cool air to the disordered state of uniform temperature. That gradient from hot to cold, from order to disorder, is what we perceive as the passage of time. Now, apply this to the universe's very first quantum state. Rovelli theorizes the primordial condition, the ultimate superposition, was a state of pure quantum entanglement with no inherent time direction. It was a perfect, featureless blur of correlations where every part was connected to every other part. A cosmic soup with no statistical gradient, no notion of hot or cold, ordered or disordered. In such a state, the concept of before and after is meaningless. The universe's first decoherence, the process of settling into a definite state, was not just about picking a set of laws. It was about creating the first and most fundamental statistical imbalance. As that vast quantum entanglement resolved, it generated a difference in quantum information across the newborn cosmos. One region, in a sense, became correlated with a slightly higher informational temperature than another. This tiny gradient was the seed. It established a direction, a flow from the more ordered, information-rich state toward the more disordered, scrambled state. We experience that flow as the relentless expansion from the Big Bang forward, as the cooling of the cosmic background radiation, as the formation of stars and their eventual death. The entire history of the universe, in this view, is the playing out of that single, initial statistical tilt created when the first superposition collapsed. The past is simply the direction of higher order, the future the direction of greater disorder. Time did not exist before that moment, it was born from it, a phantom of thermodynamics conjured from the universe's first great quantum decision to become something definite. The phantom of time born from a thermodynamic tilt reveals a universe settling into one specific reality. But what determined the shape of that reality in the first place? For string theory, the most ambitious attempt at a theory of everything, the answer lies in a cosmic garden of forking paths. This is theory number 11, the string theory landscape's quantum choice. At its heart, String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops or strands of energy. The pitch and mode of these vibrations determine what we perceive as electrons, quarks, photons, and all the forces between them. Crucially, the theory requires extra dimensions of space, often 6 or 7 of them, curled up into intricate, microscopic shapes called Calabi-Yau manifolds. The geometry of these hidden dimensions dictates how the strings vibrate, which in turn dictates the laws of physics in our observable 4-dimensional world. And here lies the profound twist. There is not one unique way to curl up these extra dimensions. Mathematical calculations suggest there are a staggering number of possible stable configurations, perhaps 10 to the power of 500 or more. This is the string theory landscape, a vast, abstract terrain of possible vacuum states, each valley representing a different universe with its own unique set of physical laws, constants, and even number of observable dimensions. Now apply this to the universe's first moment. In this framework, the primordial quantum superposition was not just over positions or energies. It was a wave function that sampled this entire cosmic landscape. The infant universe did not exist in one specific valley. It existed in a quantum haze across trillions upon trillions of them simultaneously. It was a superposition of every possible way the extra dimensions could be knotted, every possible tuning of the cosmic dials. One potential state in this superposition described a universe with 10 dimensions all expanded large. Another described a cosmos where gravity was a billion times stronger, or where electromagnetism did not exist. Our universe, with its 3 spatial dimensions, 1 time dimension, and its precise, life-permitting constants, was just one faint echo in this quantum chorus. So how did we get from that chorus to a single, clear note? The theory points to cosmic inflation, that period of fantastically rapid expansion just after the Big Bang. Inflation is framed as the ultimate decoherence mechanism. As the universe inflated, it acted like a powerful lens focusing that sprawling quantum wave function. The exponential expansion effectively measured the system, causing the wave function to localize. It cascaded down the probability slopes of the landscape, collapsing from a blur of possibilities into one specific, stable valley. The moment inflation ended was the moment our particular set of laws and dimensions became locked in, frozen into the fabric of reality as the extra dimensions curled into their specific, unchanging shape. In this view, the Big Bang was not the beginning of everything, but the moment our local cosmic neighborhood was selected from a quantum multiverse of unimaginable variety, a single reality crystallizing from a dream of infinite possibilities. Yet the selection of a specific valley in the string theory landscape implies a choice was made, a single path taken. But what if at the very beginning there were no paths at all, no smooth continuum of space or time to travel through? This leads us to Theory 12, causal set theory's quantum growth. This radical framework proposes that the fabric of reality is not a smooth, 4-dimensional sheet as Einstein described. Instead, spacetime is fundamentally discrete, composed of a vast but finite number of indivisible events like grains of sand. These events are not scattered randomly, they are connected by a single fundamental relation, causality. One event either precedes another or it does not. This network of cause and effect links, this cosmic web of before and after, is the entire structure of reality, called a causal set. The smooth geometry of space and time we experience is an emergent illusion, a blurry, large-scale picture that arises from the immense number of these causal links, much like a photograph emerges from millions of tiny pixels. Now apply this to the moment of creation. In this view, the universe's first quantum superposition was not over geometries or fields, but over the most basic possible networks. It was a haze of all potential minimal causal sets, the simplest imaginable webs of cause and effect. Picture not a glowing point, but a shimmering cloud of maybe a dozen or 100 fundamental events, with their potential causal connections flickering in and out of existence probabilistically. This was the quantum proto-spacetime, a fuzzy, probabilistic scaffolding where not even the order of events was fixed. From this primordial quantum fog, our classical universe emerged through a process physicists call sequential growth. Imagine each new fundamental event being born from the quantum possibilities of the existing set. With each new birth, a choice is made, a specific causal link to a prior event is actualized. This process resolves a piece of the initial superposition, collapsing a quantum maybe into a definite before and after. Billions upon billions of these quantum events, each one a tiny crystallization of causality, accumulated over what we now perceive as the first instance of the Big Bang. The expansion of the universe in this picture is not the stretching of a fabric, but the explosive growth of this causal network, each new event adding a new grain of spacetime and locking in a little more of the classical order we take for granted. Our smooth, continuous history is the final, stable pattern that grew from that first, fragile quantum seed of cause and effect. The smooth growth of a causal network suggests a universe built step by step, but it leaves a deeper mystery of connection unanswered. How do events separated by vast stretches of spacetime know how to relate to one another? A different interpretation of quantum mechanics offers a startling answer, one that frames the entire cosmos as a kind of agreement. This is Theory 13, the transactional interpretation's cosmic handshake. Proposed by physicist John Cramer, this model reimagines how particles interact. In standard quantum mechanics, a particle is described by a wave function that spreads out. When it is detected, that wave function collapses. The transactional interpretation adds a second, hidden wave moving in the opposite direction. Here is how it works. When an event, like an electron being emitted, occurs, it sends out an offer wave into the future. This wave explores all possible paths to potential receivers. When a receiving event, like that electron being absorbed, is present, it responds by sending a confirmation wave backward in time, along the same path. Only when the offer and confirmation waves meet and reinforce each other does a real transaction occur, locking in a definite particle event in our reality. It is a two-way quantum handshake across time. Now, apply this breathtaking idea to the universe itself. Cosmologically, the universe's first superposition can be seen as the ultimate offer wave. The initial singularity, or that quantum haze of possibilities, sent out a wave of potential futures, a spectrum of every possible cosmic history that could unfold. But an offer needs a confirmation to become real. Where could that confirmation possibly come from? The theory suggests it came from the end. The ultimate boundary condition of the cosmos, perhaps its final state at the heat death, a state of maximum uniformity and equilibrium, sent a confirmation wave backward through time. This wave from the future traveled all the way back to the beginning, selecting from that initial haze of possibilities the one specific history that would lead consistently to that particular end. Our entire cosmic timeline, from the first flash of the Big Bang to the last flicker of the final black hole, is not a one-way street from cause to effect. It is the settled transaction, the single consistent loop that resulted from this two-way quantum negotiation across 13.8 billion years. The universe we live in is the one where the offer from the past and the confirmation from the future matched perfectly, a self-consistent handshake that gave birth to reality itself. In this view, the fine-tuning of our cosmos is not an accident, but a requirement for a deal that could be struck across all of time, where the beginning and the ending are partners in creation. The cosmic handshake between past and future offers a consistent history, but it also contains a terrifying possibility hidden within its probabilities. There is a chance, however infinitesimally small, that the confirmation wave from the heat death could have validated a very different kind of reality. This leads us to a thought experiment so unsettling it becomes a theory of creation, the Boltzmann brain paradox as the universe's first quantum choice. The paradox, named for physicist Ludwig Boltzmann, arises from statistical mechanics and the nature of equilibrium. In a universe that eventually reaches a state of maximum disorder, random thermal fluctuations will still occur. Given enough time, a fluctuation could spontaneously assemble anything, even a fully formed, self-aware brain complete with false memories of an entire past. Statistically, in an eternal, lifeless cosmos, such isolated disembodied observers would be vastly more common than ordered universes with billions of stars and galaxies. So why are we not one of those random, momentary brains, hallucinating a coherent cosmos from the void? The answer may lie in that first quantum superposition. Theory 14 suggests the initial quantum state of everything was not a choice between a universe and nothing. It was a superposition between two profoundly different kinds of existence. In one branch of that wave function, the decoherence process led to the coherent, large-scale structure we see. Galaxies forming from smooth inflation, stars igniting, planets coalescing. In the other branch, the quantum dice fell differently. Decoherence favored chaos over cosmos, resulting in a reality dominated almost entirely by random, short-lived fluctuations. In that branch, Boltzmann brains pop in and out of existence constantly. Their brief, solipsistic lives the only islands of order in an eternal sea of noise. Our existence as beings embedded in a vast, ancient, and ordered universe is not a lucky accident. It is direct evidence that our specific branch of that first quantum split was the one where the laws of physics and the initial conditions strongly disfavored randomness. The fact we observe a consistent past, a shared reality, and cosmic structure on immense scales tells us that our arm of the wave function was one where decoherence acted as a powerful filter, amplifying coherence and suppressing the ghostly whispers of random minds. We are not cosmic flukes. We are the expected outcome of a quantum beginning that valued lasting structure over fleeting chaos. The unsettling possibility of Boltzmann brains reveals a cosmos where structure had to win out over chaos. But how did that structure itself first come to be? What is the substance of space that allowed for galaxies to form and light to travel? The answer might be that space itself is not a passive stage, but a dynamic, quantum entity that had to crystallize. This brings us to Theory 15, the quantum gravity model of cosmic solidification. In this radical picture, the fundamental fabric of reality is not a smooth continuum. Instead, think of space as a vast, dynamic network, a cosmic graph. At the most basic level, reality consists of an enormous number of simple points or nodes. In the beginning, these nodes were not arranged in any orderly way. They were all connected to each other in a dense, chaotic web, a state of maximum connectivity and quantum fluidity. Every point was linked to every other point directly, creating a state without distance or direction, a kind of cosmic soup of pure relationship. This primordial network was not in one definite configuration. It existed in a quantum superposition of all possible connection patterns, a shimmering haze of potential geometries. This was the universe's first state according to gravity, a hot, buzzing hive of pure quantum connection. Then something remarkable happened, a cosmic phase transition. As the universe expanded and cooled, analogous to water freezing into ice, this quantum graph underwent a profound change. The highly connected, fluid network became unstable. The superposition began to resolve, not randomly, but into a configuration that minimized energy. The countless, chaotic links between nodes began to snap, reforming into a new, orderly pattern. The graph froze. It crystallized into a regular, repeating lattice structure, much like the atomic lattice in a crystal. This new lattice had a specific, stable architecture. one that gave rise to the three spatial dimensions we move through today. In this model, the three dimensions of space are not fundamental. They are an emergent property of how this quantum graph froze. The lattice spacing, the distance between connected nodes, became what we perceive as the Planck length, the smallest possible unit of distance. The photons of the cosmic microwave background, that ancient afterglow from the universe's infancy, might carry a faint echo of this monumental event. They could be the residual vibrations, the cosmic ring, from the moment space itself solidified. The uniform hum we detect from all directions is not just the cooled remnant of a hot plasma. It could be the fossilized sound of the quantum graph settling into its rigid, classical form, a permanent whisper of the moment possibility became place. Space itself, once a frozen crystal lattice, presents a stable stage for reality to play out. But what is the deeper nature of the connections that hold that stage together? A revolutionary idea born from the study of black holes suggests that the most fundamental link in the cosmos is not a force, but a tunnel. This is Theory 16, the ER equals EPR conjecture and the wormhole genesis. The equation itself is deceptively simple. ER equals EPR. It links two of Einstein's most famous ideas, but from opposite ends of his career. ER stands for Einstein-Rosen bridges, the formal name for wormholes, hypothetical tunnels through spacetime connecting distant locations. EPR stands for Einstein-Podolsky-Rosen, the famous thought experiment highlighting the spooky action at a distance of quantum entanglement, where two particles remain mysteriously connected regardless of the space between them. For decades, these were seen as separate, unrelated phenomena, one from general relativity and one from quantum mechanics. The ER equals EPR conjecture, proposed by physicists like Juan Maldacena and Leonard Susskind, makes a breathtaking claim: they are the same thing. Quantum entanglement, that spooky connection, is physically manifested by a microscopic wormhole linking the particles. The particles are not communicating faster than light. They are, in a geometric sense, touching through a hidden shortcut in the fabric of reality. Now, take this radical equivalence and scale it up to the absolute beginning. Theorists propose that the universe's first quantum superposition was not just a haze of possibilities. It was a state of maximum, universal entanglement. Every potential piece of the future cosmos was quantum mechanically linked to every other piece in a dense, impenetrable web. According to ER equals EPR, this means the infant universe was not a point, but a seething foam of unimaginably tiny quantum wormholes, each one representing a thread of entanglement in that primordial quantum tapestry. Space, as we know it, did not exist yet. What existed was pure connection, a labyrinth of microscopic bridges. The Big Bang, in this view, was not an explosion in space, but an explosion of space. It was the catastrophic disconnection, the pinching off of that all-encompassing wormhole network. As the universe underwent its first decoherence, those quantum threads were severed. But they did not vanish. The energy and structure bound up in those countless connections had to go somewhere. In a monumental geometric transformation, the fabric of the wormholes themselves unfurled and stretched, converting into the smooth, classical, three-dimensional spacetime we inhabit. The places where wormholes were most densely packed became the seeds for the first large-scale structures, the gravitational wells that would one day pull together into galaxies and clusters. The cosmic microwave background's faint temperature variations could be the fossilized imprint of that original wormhole foam, a snapshot of the entanglement pattern moments before it crystallized into distance and geometry. In this profound vision, the universe began not as a singularity of infinite density, but as a singularity of infinite connection, a quantum handshake so intense it forged the very stage of reality when it finally let go. The wormhole genesis paints a picture of a universe born from pure connection. But what if that connection served a deeper, almost biological purpose? Lee Smolin's theory of cosmological natural selection introduces a startling metaphor: universes that evolve. In this view, black holes are not cosmic dead ends, but cosmic wombs. When a star collapses into a black hole, the singularity at its heart, that point of infinite density where our laws of physics break down, becomes a gateway. According to Smolin, a new universe can be born from that singularity, with its fundamental constants slightly tweaked, mutated versions of the parent universe's laws. Universes that produce more black holes have more offspring, passing on their traits in a multiversal game of natural selection. This alone is a revolutionary idea, but we must now add the essential quantum layer to see its full power at the moment of creation. Inside every black hole singularity, the conditions are not just extreme, they are fundamentally quantum. The birth of a daughter universe is not a definite, classical event. It begins as a quantum superposition. Within that seething gravitational maelstrom, the new cosmos exists in a haze of possibilities, a wave function sampling every potential set of physical constants, every conceivable twist of the extra dimensions. But this sampling is not random. The properties of the parent universe, its specific laws and constants, act as a powerful bias. They influence the probability distribution of the offspring's laws, making some outcomes in that quantum haze far more likely than others. A universe with strong nuclear forces might make stellar black holes more probable, and that trait could be passed on, making certain branches of the superposition more robust. Now, apply this quantum reproductive logic to our own origin. Our universe, from its very first instant, was likely one branch of a vast superposition born inside a black hole in a prior cosmos. That initial quantum state contained the potential for countless different cosmic rulebooks, but the genetic bias from its parent made certain outcomes, like a universe with 3 stable spatial dimensions and forces capable of forging heavy elements in stars, more probable. As our cosmos decohered from that quantum fog, the branch that resolved was precisely the one tuned to produce an abundance of black holes. The precise strength of gravity, the exact value of the cosmological constant, even the existence of atoms like carbon, all may be finely tuned not for life, but for stellar collapse and gravitational reproduction. Our reality is not necessarily the most hospitable one, it is the most fertile one. The galaxies we see are not just islands of stars, they are cosmic nurseries ensuring this branch of the quantum multiverse continues to propagate, a single, wildly successful lineage in an eternal tree of evolving possibilities. But what if the very rules of reasoning we used to understand the cosmos were part of its first great choice? Our classical world runs on a simple, binary logic. A statement is either true or false. A particle is either here or there. This is Boolean logic, the foundation of computers and clear thought. Yet at the quantum scale, this crisp either or breaks down. A particle can be here and there until observed. To describe this, physicists have turned to a different kind of mathematics, Topos theory, which provides a framework for alternative logical systems. Theory 18 proposes that the universe's first state was not governed by our familiar true-false logic at all. It was ruled by a true quantum logic, where the law of the excluded middle simply did not apply. In that primordial haze, statements about reality were not true or false. They existed in a superposition of truth values, a fuzzy spectrum of maybe. A proposition like the universe has 3 spatial dimensions was not definitively true or false. It had a certain probability of being true, and a certain probability of being false, and those probabilities themselves were part of the quantum wave function. The cosmos was in a state of logical ambiguity, a place where contradictions could coexist without conflict. This was not just a superposition of physical states, but a superposition of possible logics, of different ways for reality to make sense. The emergence of our classical universe, then, was not merely a physical decoherence. It was a logical crystallization. As the infant cosmos cooled and expanded, it underwent a profound metaphysical phase transition. The fuzzy, probabilistic logic of the quantum beginning resolved, collapsing into the sharp, binary, yes-no logic of Boolean algebra. This transition defined everything that followed. The moment a statement like a particle has a position became definitively true was the same moment the arrow of time was born, creating a clear sequence of cause and effect from a soup of ambiguous potential. The very nature of objective reality, the world of definite objects and properties we take for granted, is a consequence of this shift. We do not live in a universe that merely chose its physical constants. We live in the one branch of possibility that chose a specific, rigid way to think. The ghost of that first logical superposition still haunts the quantum realm, a reminder that our clear, classical world is built upon a foundation of profound and ancient ambiguity. Our clear, classical logic feels absolute, a foundation for all reality. Yet it emerged from a quantum fog of maybe, a reminder that the rules of existence themselves were once undecided. This leads to a modern question that reframes the entire mystery. What if our universe is not fundamental at all, but a kind of computation? This is Theory 19, the simulation hypothesis as a quantum program. The idea that we might live in an artificial reality, a sophisticated simulation run by a far more advanced civilization, has moved from science fiction to a serious philosophical argument. But if this is true, what kind of computer could possibly run something as vast and detailed as a cosmos? The answer points directly back to our quantum beginnings. A classical computer, built on ones and zeros, would struggle unimaginably to simulate every particle in a universe. The processing power required would be astronomically, impossibly large. But a quantum computer operates on an entirely different principle. It does not calculate one answer at a time, it calculates all possible answers simultaneously, holding them in a state of quantum superposition. This is the key. If our reality is a simulation, its most efficient, most elegant base code would not be classical, it would be quantum mechanical. In this view, the universe's first superposition was not a physical event in a void. It was the loading of the initial quantum program state. The moment of creation was the moment the simulation booted up, and its entire memory buffer was initialized not with a single set of data, but with a coherent quantum superposition of every possible cosmic history. Every potential arrangement of galaxies, every variation of physical constants, every possible timeline from the Big Bang forward existed in that quantum cache, all at once, waiting to be processed. Our Big Bang was not an explosion of energy, but the act of running the program. The moment the simulation began its first computational cycle, it was forced to take a measurement. It had to query that vast quantum buffer to produce a definite output for the first frame of reality. That act of measurement collapsed the quantum possibilities. From the near-infinite potential histories in the buffer, one consistent classical timeline was selected, not randomly, but according to the programmed rules and initial conditions of the simulation's code. The universe we perceive is that single, rendered timeline being calculated frame by frame, with the illusion of a past generated on the fly from saved data. The eerie quantum behaviors we observe, from entanglement to superposition, are not bugs, they are features, glimpses of the underlying quantum architecture of the simulation's operating system. In this scenario, we are not just living in a simulated universe. We are living in the one specific history that resolved when the quantum program first compiled itself from a dream of all possible worlds into the single, streamed reality we are now processing. The universe's first quantum program may have rendered our reality, but what was the source code it compiled from? Beneath the simulation, beneath the logic and the connections, lies a more elegant possibility. The newborn cosmos did not start with four distinct forces: gravity, electromagnetism, and the strong and weak nuclear forces. It began with a single, perfect unity. This is Theory 20, the symmetry-breaking cascade, where the universe's first superposition was one of pure, undifferentiated potential. In that unimaginably hot, dense first instant, all the forces we know were seamlessly merged into one fundamental interaction. The quantum state was a perfect symmetry, a superposition where every force was every other force, and every particle type was blurred together. There was no difference between a quark and a lepton, between a photon and a gluon. Reality was a single, harmonious quantum chord vibrating at the maximum possible energy. This perfect symmetry, however, was inherently unstable, like a pencil balanced perfectly on its tip. As the universe expanded and cooled, it could not remain in that exalted state. It underwent a series of profound phase transitions, each one a cosmic symmetry breaking. Think of water. As steam cools, it undergoes a phase transition, condensing into liquid water. Cool it further, and it freezes into solid ice. Each transition breaks a symmetry. The uniform gas condenses into droplets with a definite surface. The liquid freezes into a rigid crystal with a specific lattice orientation. The universe did the same, but the symmetries it broke were far more fundamental. The first transition happened perhaps a trillionth of a second after the beginning. As the cosmos cooled past an unimaginable temperature threshold, the perfect symmetry of the unified force shattered. The gravitational force decoupled, peeling away from the grand unified force that contained the other three. This was not a smooth separation, it was a quantum collapse. The superposition of all forces resolved, with gravity crystallizing out as a distinct entity. In that moment, the geometry of spacetime itself gained its own independent character. The cascade continued. A fraction of a second later, another cooling threshold was crossed. The strong nuclear force, the glue that binds atomic nuclei, broke free from the electroweak force. Another layer of quantum possibility collapsed, locking in the rules for how quarks would forever be bound into protons and neutrons. Finally, as the universe cooled further, the last great symmetry broke. The electroweak force split into the two distinct forces we know today, electromagnetism and the weak nuclear force. With each breaking, a new set of particles gained their unique identities. The photons, the W and Z bosons, the Higgs boson, all emerged from the quantum fog as definite entities with specific roles. This entire majestic cascade, from perfect unity to the four forces of our modern world, was the universe's great act of decoherence on a cosmic scale. That initial, perfect symmetry was the ultimate quantum superposition. The evolution of the cosmos is the story of that superposition cooling, stabilizing, and collapsing in stages. Each phase transition a decision that carved our specific reality from a more potent, more ambiguous past. The forces we measure so precisely today are not eternal truths. They are the frozen remnants of the universe's first and most consequential series of quantum choices. The symmetry-breaking cascade gave us our forces, but what was the substance being transformed? Information itself may be the answer, the most fundamental currency of reality. Theory 21 proposes we treat the entire cosmos not as a collection of things, but as a quantum information processor. In this view, the initial singularity was not a point of infinite density in the classical sense. It was a state of maximal quantum information density, a seething, probabilistic foam of qubits. A qubit, or quantum bit, is the fundamental unit of quantum information. Unlike a classical computer bit, which is definitively a 1 or a 0, a qubit can be a 1, a 0, or any probabilistic mixture of both simultaneously. That initial state was a cosmos-sized qubit foam, a chaotic, super-dense soup of every possible yes, no, and maybe, all tangled together in quantum entanglement. This was the universe's first superposition, a state representing all possible programs, all possible sets of instructions that this cosmic quantum computer could potentially run. One potential program in that foam might have described a universe that immediately collapsed. Another might have described a cosmos of pure, featureless light. Our universe, with its specific laws and eventual complexity, was just one potential algorithm flickering in that primordial chaos. The Big Bang, then, was not an explosion of matter into space. It was the initiation of the computation. The rapid expansion of the universe was the physical manifestation of information decompression and processing. As space stretched, the incredibly dense qubit foam began to untangle, its quantum information spreading out and interacting. This processing of information through quantum gates is what we perceive as the evolution of physical laws and the formation of particles. In the earliest, hottest moments, the computation was wild and unstable, a frenzy of probabilistic operations. But just as in any complex system, certain computational pathways proved more stable than others. Feedback loops emerged. Certain patterns of information processing began to reinforce themselves, creating structures that were resistant to the surrounding quantum noise. Our specific physics, the precise values of constants and the rules governing particles, is not an arbitrary input. It is the output, the final, stable data pattern that resulted from one particularly robust and complex computation running on the hardware of spacetime. The galaxies, stars, and planets we see are not just physical objects. They are the long-term, classical results of that initial quantum calculation, the cosmic printout from a program that successfully ran for 13.8 billion years without crashing. In this profound vision, we are not just made of stardust. We are made of processed data, living in the one cosmic story that successfully computed itself into existence from a quantum sea of infinite possibility. That initial cosmic computation suggests a universe with a single, definite history. Yet a different interpretation of quantum mechanics argues reality was always this definite, even from the very first moment. This is Theory 22, the de Broglie-Bohm pilot wave cosmology. To understand it, we must revisit the double-slit experiment. In the standard view, an electron is a smeared-out wave of probability until it is measured. Then it collapses to a point. The pilot wave theory, developed by Louis de Broglie and later David Bohm, offers a radically different picture. Here, the electron is always a real particle with a definite position, like a tiny speck. But it is not alone. It is guided by an invisible, non-physical wave that fills all of space, the pilot wave. This wave does not collapse. It evolves according to the Schrödinger equation, exploring all possible paths. The particle itself, however, rides just one specific path, pushed along by the forces exerted by this guiding wave. The particle is like a surfer, and the pilot wave is the ocean swell, determining exactly where the surfer will go, even though the swell itself extends across the entire bay. Now, scale this ideal up to everything. Cosmologically, the entire universe is that surfer. It has always been a single, definite entity with a specific configuration, even at the moment of the Big Bang. But what guided it? The answer is the wave function of the universe itself, the single, gigantic pilot wave that emerged from the initial conditions. In this view, the universe's first superposition was not in the physical cosmos, but in this guiding wave. That primordial wave was a probability field containing the blueprints for every possible universe configuration, every potential arrangement of matter and energy across all of space and time. It was a quantum atlas of all possible realities. Our specific universe, the particle, has always been on one specific trajectory through this atlas. It did not branch or split. It was simply guided, moment by moment, by the contours of this all-encompassing probability landscape. The apparent randomness of quantum events, from the decay of an atom to the formation of a galaxy, is not true randomness. It is the result of our ignorance of the exact initial conditions of the universe particle and the subtle, hidden variables within the pilot wave that steer its path. The Big Bang, then, was not the collapse of possibilities. It was the moment the cosmic surfer began its ride, propelled onto a specific, predetermined course by the first swell of the ultimate quantum wave. While this provides a comforting sense of a single, objective history, it demands a hidden layer of reality, a guiding hand that forever remains just out of sight, choreographing the entire cosmic dance from behind the curtain. A predetermined cosmic surfer offers one path through the quantum atlas, yet it implies the entire journey was set from the start. But what if the destination itself reached back to shape the beginning? This is Theory 23, the omega point cosmology's quantum telos. Proposed by physicist Frank Tipler, the omega point is not a place, but a future state, a final boundary of reality. As the universe approaches its ultimate fate, perhaps a catastrophic crunch or an infinitely prolonged expansion, the total amount of information processing that can occur becomes infinite. In this ultimate future, consciousness in some form could become omnipresent and omniscient, a kind of cosmic mind that encompasses all of existence. Now, view this through a quantum lens. From this perspective, the universe's initial wave function was not a random quantum menu. It was a precisely tuned instrument, a quantum state designed with one ultimate purpose: to guarantee the inevitable evolution toward that omega point. The first great superposition, therefore, was not a haze of all possible histories. It was a constrained, filtered set of possibilities. It contained only those potential cosmic timelines that were logically consistent, that possessed the exact right constants and initial conditions to unfailingly steer the cosmos toward that final, self-aware state. Any quantum branch that led to an early collapse, a barren void, or a dead end of eternal silence was simply not present in that initial wave. They were quantum impossibilities from the very first instant. In this breathtaking framework, the Big Bang was the opening move in a quantum computation of unimaginable scale, a computation whose only acceptable answer is the universe's own ultimate self-consciousness. The beginning and the end are not separate events in a linear chain. They are quantum entangled, locked in a loop of cosmic necessity. The fine-tuning we observe in the laws of physics is not an accident, nor is it for our benefit alone. It is the signature of a universe that was, from its first quantum breath, destined to wake up. The cosmic microwave background, the distribution of galaxies, the very existence of atoms, all are the intermediate steps in a quantum equation solving for its own awareness. We, and any other conscious beings, are not mere passengers. We are integral components of this computation, nodes in the network that is gradually weaving itself into the omega point. The universe did not just happen to produce observers. It was quantum mechanically compelled to, with its first superposition already whispering the final, conscious thought at the end of time. The universe's first quantum state may have been a perfect, silent mirror. Theory 24 introduces a profound symmetry, supersymmetry, which proposes that every fundamental particle we know has a hidden twin, a superpartner. An electron would have a selectron, a quark would have a squark, a photon would have a photino. In our world today, this symmetry is utterly broken. These superpartners are so incredibly massive we have never detected them. But at the very first instant in that searing heat of the Big Bang, physicists believed this symmetry was perfect and unbroken. Every particle existed in a quantum superposition with its superpartner. They were not distinct entities, they were two faces of the same quantum coin, flickering between identities in a state of perfect balance. This was a universe of ultimate order, where matter and the forces that govern it were reflections of each other in a quantum haze. The decoherence of this state was one of the most monumental events in cosmic history. As the universe cooled, that perfect supersymmetry shattered. The superposition collapsed, and the superpartners gained immense mass, effectively hiding from our current low-energy reality. The energy released in this cosmic symmetry breaking was staggering, and it is this energy that many theorists believe powered the period of hyper-expansion we call cosmic inflation. It was the engine that blew up a quantum seed into a macroscopic cosmos. But the echoes of that first supersymmetric state did not vanish entirely. The lightest of these superpartners, often called the neutralino, would have been stable. Billions upon billions of them would have been frozen out as the universe cooled, streaming through space unaffected by light or electromagnetism. This, many physicists argue, is the identity of dark matter. The ghostly halo that holds our galaxies together, the invisible scaffolding of the cosmos, may be the direct remnant, the cosmic ash, from the decoherence of the universe's first and most perfect quantum symmetry. We search for dark matter today not just to solve a modern mystery, but to touch a relic from the moment reality chose to become the asymmetric world we know. That perfect symmetry left a ghostly halo of dark matter, but it also left behind a far more perplexing puzzle, one that threatens to unravel our entire understanding of gravity and quantum theory. This is the cosmological constant problem, and its solution may lie in the universe's first great quantum filter. The cosmological constant is a term in Einstein's equations representing the energy of empty space, a kind of anti-gravity pushing the universe apart. Quantum field theory predicts this vacuum energy should be enormous, 120 orders of magnitude larger than what we observe. Our universe's expansion is accelerating, but at a rate so gentle it seems almost lazy compared to the explosive repulsion the math demands. This discrepancy is the worst prediction in all of physics. Theory 25 offers a quantum solution born from desperation and elegance. It suggests the early universe did not have one specific value for this vacuum energy. It existed in a quantum superposition of all possible values, from negative infinity to positive infinity. The wave function of the cosmos was a probability spread across every conceivable level of cosmic repulsion. In the vast majority of these quantum branches, the dice fell catastrophically wrong. If the cosmological constant was too large and positive, the repulsive force was so violent it ripped spacetime apart in an instant. A cosmic inflation gone mad that tore every atom to shreds before any structure could form. If the value was too large and negative, the vacuum energy acted like an irresistible cosmic glue, causing the entire universe to collapse back into a singularity almost immediately after the Big Bang. These branches were cosmic dead ends, universes that blinked out of existence in a fraction of a second. Our reality exists in the razor-thin slice of that initial quantum superposition where the value happened to be almost exactly zero. Not perfectly zero, as our observed acceleration shows, but so infinitesimally small it allowed for the slow, graceful expansion needed for galaxies to coalesce and life to eventually emerge. How did this improbable selection occur? Physicists like Sidney Coleman and Frank de Lucia proposed a mechanism called the Coleman-de Lucia instanton, a kind of quantum tunneling event on a cosmic scale. In the frothing quantum foam of the beginning, our universe could have tunneled from a high-energy, unstable vacuum state into our low-energy, nearly flat one. The act of tunneling itself acted as a filter, a quantum sieve that only allowed universes with a tiny cosmological constant to successfully nucleate and inflate into a stable cosmos. Alternatively, the universe's own wave function could have interfered with itself, with branches of high vacuum energy destructively interfering, canceling each other out, while the branch with near-zero energy constructively reinforced itself into existence. In either case, our cosmos is not just unlikely. It is the quantum survivor, the one shimmering thread of possibility that did not instantly self-destruct. The gentle push of dark energy we measure today is not a flaw, but a signature, the faintest echo of the cosmic lottery we somehow won in that first instant, when nearly every other version of reality tore itself apart. This faint afterglow of our quantum lottery win might be more than just leftover heat. It could be a memory of light itself, captured at the very dawn of reality. Theory 26 offers a beautiful and metaphorical vision, the phosphorescent universe model. In our world, a phosphorescent material, like the paint on a glow-in-the-dark star, does something remarkable. It absorbs light energy, storing it within its atomic structure. Then, in the darkness, it slowly releases that energy as a soft, persistent glow. The light we see later is not a new creation. It is the delayed emission of the light it once held. Now, apply this poetic concept to the cosmos. In this view, the universe's first quantum superposition was not a chaotic foam or a silent symmetry. It was a state of pure, brilliant potential, a cosmic phosphor charged to its absolute limit. That initial state glowed not with physical light as we know it, but with the light of pure possibility. Every future galaxy, every particle interaction, every law of physics existed as a shimmering potential within that radiant haze. The superposition was this all-encompassing glow, where every possible history was equally bright, equally present, and equally real. Then came the transition. The Big Bang was the moment this phosphorescent potential began its slow, majestic release. It was not an explosion into darkness, but the beginning of a cosmic dimming into definition. As the universe expanded and cooled, that brilliant, unified glow of all possibilities began to resolve. Each actualized event, the formation of the first force, the creation of the first particle, the ignition of the first star, was a single photon of definite reality being emitted from that vast reservoir of potential. The process was not instantaneous. Just as a glow in the dark star fades slowly, the universe's potential has been steadily releasing for 13.8 billion years, crystallizing maybe into probability into history. And what of the cosmic microwave background, that uniform bath of microwaves that permeates all of space? In this model, it is not the cooled remnant of a hot plasma, but the final, faint afterglow. It is the coolest, most stretched-out light remaining from that initial brilliant state of quantum potentiality. The tiny temperature variations we map across the sky are not wrinkles in space-time, but the last, fading impressions of the specific pattern in which the potential finally released. The faint fingerprint of how the glow chose to dim into the structured cosmos we see today. We are living in the long, slow fade of the universe's first and most magnificent light, watching as the last echoes of its infinite potential still whisper to us from the void. The mathematics that may describe creation is not about numbers or equations, but about relationships and transformations. This is Theory 27, the category theory of quantum genesis. Category theory is often called the mathematics of mathematics, a framework that strips ideas down to their most abstract essence. It studies objects and the arrows or morphisms that connect them. The power lies not in what the objects are, but in how they can change into one another. To apply this to the beginning, theorists propose that the primordial state of everything was not a point or a wave, but a terminal object in a cosmic category. In this abstract sense, a terminal object is a unique state from which every other possible state can be reached by one, and only one, kind of transformation. It is the ultimate starting point, the blank canvas from which every painting can be uniquely derived. That first indescribable moment was this silent, featureless terminal object. Its initial quantum superposition was not a haze of things, but a haze of possible changes. It was the set of all possible morphisms, all conceivable arrows of transformation, radiating out from that silent origin. Each arrow represented a potential pathway to a new state, a new configuration of reality. One morphism might lead toward a state where time flows backward. Another might lead to a universe of 10 spatial dimensions. Another might describe a cosmos made entirely of dark energy. Our universe is not one of the objects in that first blur. It is one specific, consistent sequence of these morphisms, a particular chain of transformations that, when composed in just the right order, resulted in a stable, self-consistent category. This stable category is what we experience as physics. With its objects we call particles and its morphisms we call forces. The act of the Big Bang was the selection of that specific compositional path from the quantum soup of all possible arrows. The fine-tuning we observe is the signature of a compositional chain that closed back on itself logically, creating a categorical loop stable enough to persist for billions of years. In this profoundly abstract vision, the universe did not begin with a thing, but with the potential for change, and our entire history is just one elegantly consistent story written with the arrows of transformation. This abstract dance of arrows and morphisms points toward a universe born from pure relationship. Yet the deepest relationships we know are those of thought and intention. Some theories dare to ask if the cosmos itself might be the product of a mind. This brings us to Theory 28, a philosophical journey often called the quantum gravity in the brain of God. It is crucial to frame this not as a religious doctrine, but as a profound metaphor for a transcendent creative principle. In this view, the universe's first quantum superposition did not exist in a void or a quantum field. It existed within an infinite, transcendent consciousness, a cosmic mind contemplating every possible form of existence. That initial haze of all possibilities was not a chaotic foam, but a divine thought experiment, a boundless imagination holding every potential law, every potential story, every potential reality in a state of simultaneous consideration. This cosmic mind is not a bearded figure in the sky, but the ultimate ground of being, the source from which logic, mathematics, and possibility themselves emerge. The act of creation, then, was not a violent explosion, but an act of focused attention. The observation, the intention of this cosmic consciousness, collapsed that infinite superposition. But it did not collapse it into a single, rigid universe. Instead, it collapsed the wave function into a manifold, a rich tapestry of interwoven realities, each with its own degree of creative freedom. Some branches of this tapestry might be highly constrained, with fixed, clockwork laws allowing for little novelty. Others might be too chaotic, dissolving into noise before any structure can form. Our universe occupies a very special place in this manifold. Its physical laws, the specific constraints chosen from that first divine thought, are precisely the set that allows for a remarkable phenomenon: the emergence of self-aware, creative beings within the grand design. The constants are not arbitrary. They are the necessary conditions for a universe complex enough to host creatures who can themselves observe, question, and create. We are not accidental byproducts. In this metaphorical framework, we are a feature of the design, the means by which the cosmos becomes aware of itself. The fine-tuning for life is not a lucky break. It is the signature of a universe intentionally shaped with the potential for interiority, for experience, for meaning. The quantum weirdness we still detect, the spooky connections and probabilistic underpinnings, are echoes of that original, boundless state of mind, reminders that our classical, solid world is a crystallization of a vaster, more fluid thought. This theory suggests we live in a cosmos that is, in a very real sense, a shared dream, a stable reality dreamed into being so that something within it could eventually wake up and wonder back at the dreamer. That shared cosmic dream, however profound, must have been written in a specific kind of code. The structure of that code may be the most beautiful pattern in all of mathematics, a pattern that repeats itself at every scale. Our universe might be the frozen echo of an infinite, shimmering kaleidoscope. This is Theory 29, the fractal holographic superposition, a breathtaking fusion of two of our most powerful cosmic ideas. We have already explored the holographic principle, where our three-dimensional reality is a projection from a two-dimensional surface of information. And we have glimpsed fractals, those intricate shapes where the same pattern repeats whether you zoom in 1,000,000 times or zoom out 1,000,000 times, like a coastline or a snowflake. Now, combine them at the moment of creation. In this view, the universe's first quantum state was not just a hologram, it was a fractal hologram. The information encoded on that primordial two-dimensional boundary was not random. It was arranged in a pattern of exquisite self-similarity. At every conceivable scale, from the unimaginably tiny Planck length to the vastness of the entire cosmic horizon, the same fundamental informational pattern repeated. This was a quantum superposition with a built-in symmetry of scale, a holographic blur where every part reflected the whole. One potential state in this superposition might have been a fractal where matter clustered in a specific branching pattern. Another might have been a fractal of pure, swirling energy. Our cosmos, in all its potential forms, was contained within this infinite, recursive quantum design. Then, decoherence struck. As the universe cooled and expanded, that perfect fractal symmetry had to break. A universe with a truly infinite fractal structure would look the same at all scales, which ours clearly does not. A galaxy does not look exactly like a star, which does not look exactly like an atom. Yet the break was not clean. It was a partial freezing. Think of a snowflake forming in a cloud. As it falls through layers of varying temperature and humidity, its growth pattern changes. The final snowflake is not a perfect mathematical fractal, but it carries the unmistakable, branching signature of its fractal origin. Our universe did the same. As it decohered from that quantum fractal haze, it froze into a specific snapshot, one moment in the dynamic evolution of that infinite pattern. The imprint of its origin is everywhere. Look at the cosmic microwave background, that baby picture of the universe. Its temperature fluctuations are not random. They follow what physicists call a scale-invariant pattern. This means the statistical distribution of hot and cold spots is nearly identical whether you look at patches of sky that are 1 degree across or 10 degrees across. That is the fingerprint of a fractal origin, a faint echo of that initial self-similar quantum code. Look further at the large-scale structure of the universe today. Galaxies are not scattered randomly like salt on a table. They form an immense cosmic web, a vast network of filaments and clusters with huge voids between them. Computer simulations show this web has a fractal-like quality over certain scales, a relic of the gravitational growth of those initial, scale-invariant seeds from the Big Bang. In this profound synthesis, our entire cosmos is not a unique creation. It is a single frame, a frozen moment, in the endless recursive dance of a quantum fractal hologram. We are not living in a simulation of a universe, but in the decohered snapshot of a pattern that once held infinity within every point. The infinite fractal pattern points to a code, but what is the nature of that code itself? The final theory takes us to the ultimate frontier of abstraction, where reality is not just described by mathematics, but is mathematics. This is Max Tegmark's mathematical universe hypothesis, and when we apply it to the quantum beginning, we arrive at a staggering conclusion. Theory 30 proposes that the universe's first and only true superposition was over all possible mathematical structures. Before time, before space, before anything we would call physical, there existed a quantum haze of pure abstraction. This was not a superposition of energies or particles, but of every conceivable self-consistent mathematical system, from the simple rules of arithmetic to the dizzying complexities of infinite-dimensional algebras. One potential state in this haze was the structure of Euclidean geometry. Another was the system of complex numbers. Another was the set of all possible chess games. Our cosmos, with its 4 forces and quantum fields, was just one particularly rich and complex mathematical structure, flickering in that ultimate quantum ensemble. In this view, the Big Bang was not a physical event. It was the moment a specific mathematical structure decohered from the quantum blur of all possibilities and gained what we perceive as physicality. The laws of physics we spend our lives measuring are not imposed from the outside. They are the inherent theorems, the logical consequences, of this particular mathematical entity we happen to inhabit. The speed of light is a constant in its equations. The charge of an electron is a defined parameter. Gravity is a curvature in its geometric fabric. These are not choices made by a creator. They are inevitable features of the structure, just as the angles of a triangle in Euclidean geometry always add to 180 degrees. So why this structure and not another? The answer may lie in stability and complexity. In that initial quantum ensemble, most mathematical structures were likely barren or self-contradictory, collapsing instantly. Our specific structure was one of the rare, stable ones, a coherent set of axioms and rules complex enough to allow for substructures within substructures, for patterns that could encode information, evolve, and ultimately become self-aware. We are not living in a universe that runs on math. We are living inside a specific mathematical object that became real. Our consciousness, a fleeting pattern of information processing within its eternal, logical truths. The cosmic microwave background is its opening line. Every galaxy is a paragraph in its proof. And our quest to understand the cosmos is simply this mathematical structure, through us, beginning to comprehend its own beautiful, inevitable form. From perfect symmetry to fractal codes and mathematical structures, these 30 theories paint a breathtaking portrait of creation. They differ in their details, their mechanisms, and their starting assumptions, yet they all point toward a single, staggering theme. Our universe likely did not begin as a definite, singular event. It emerged from a quantum haze, a shimmering cloud of maybe. Before there was a here or a there, a then or a now, there was a superposition, a probability wave containing the seeds of every possible reality. The cosmos we call home is not the only story that could have been told. It is simply the one that resolved from that first great quantum question. This perspective fundamentally reframes our place in the grand scheme. We are not accidental inhabitants of a finished, mechanical clockwork. We are the universe itself, in one particular branch of that ancient probability wave, slowly becoming aware of its own existence. Every thought we have, every question we ask about the stars, is the cosmos peering back into its own mysterious origins, trying to understand the dream from which it awoke. The search for the first quantum moment is more than physics. It is the story of reality seeking its own reflection. Which of these 30 visions resonates most deeply with you? Was it the cosmic handshake of the transactional interpretation, the evolutionary pressure of cosmological natural selection, or the stark, beautiful logic of the mathematical universe? Let us know in the comments below which theory you find most plausible or most poetic. And if you want to continue exploring the profound mysteries at the edge of space and time, be sure to subscribe. Our journey through the quantum foundations of reality has only just begun.